We'll continue then with our next speaker, and that's Arushi Nath, and she presented to us last month on the Didymos asteroid system impact. And she spoke about what happened before the impact. Tonight she's going to talk to us about after the impact. So take it away, Arushi.
Great, thank you. So my name is Arushi, and I'm in downtown Toronto. And today I'm going to be talking about my photometric observations of the Didymos system after the impact. So just a quick recap on the DART mission. So this was a planetary defense test mission launched to the Didymos asteroid system to try and test out the deflection method of a kinetic impactor. So on 26th of November, the DART mission impacted the moonlet of Didymos called Dimorphos, and it was able to successfully impact, which was actually the first goal of this mission. But there's also three other goals of the DART mission. The second one was to cause at least a 73-second change in the orbital period of the Dimorphos around Didymos, and this was definitely very successful. The orbital period was changed over 25 times the predicted amount, so it was changed by around 32 minutes. The third goal was to measure the change in the binary period to an uncertainty of 7.3 seconds or less. This goal was also achieved. And the fourth goal, which is still pending right now, is to measure the momentum transfer efficiency of the DART impact. So both citizen scientists and professional astronomers have been observing the Didymos system before impact to measure the baseline of the rotational and orbital period of the Didymos system. During the impact, to measure the change in magnitude of the Didymos system, as well as to see any tails that are coming from the ejecta of the impact, and also post-impact to measure the changes in the orbital period and other changes that might have happened after the DART mission impacted. So these are different sources from different observatories that have captured the Didymos when it was impacted by the DART. So this is from space telescopes like the Hubble and the James Webb, but also from ground-based telescopes like the Atlas and the LCO Observatory. I was also able to find ultraviolet information from the NASA Swift Space Telescope during the impact. So during the impact, there was a sharp raise in radioactivity caused by the impact. And actually, in the bottom right figure, you'll see this change, and you'll see two circles on the image. The red one is of the Didymos, and the other one above it, orange, is for the background noise. So the DART mission team has also been observing the Didymos system every day after the impact. But I want to point out two interesting days, this September 29th and October 4th, where they were also able to include mutual events in their observations. And you can see from the bottom two graphs, in gray, you can see the arrow saying the expected mutual event time based on the previous period of 11 hours and 55 minutes. But from the new orbital period of 11 hours and 23 minutes, you can see the mutual event was observed in a different place, both on September 29th and on October 4th, showing the successful change in the orbital period. So how do you measure the differential photometry of asteroids? So first, telescopes have a camera attached to them, and this camera is receiving photons from the sky. And the more photons one pixel receives, the brighter it will be. And if we create a boundary of the object that we're looking at, in this case, Didymos, then we're able to find the total brightness of the whole object. In the left image, you can see that there's three circles here. In the middle, this is where we're actually observing the object. And on the outer ring, This is nothing to do with the object actually. This is just observing the noise that's coming from the image, so that we know how much noise is in the observation, and we can subtract it to find the actual magnitude of the Didymos. So looking at the magnitude of the Didymos across the time period, we can find great light curves of the Didymos. And what do these light curves give us? Well, they can definitely first give the time period of mutual events. So this includes the primary occultation, which is when Dimorphos goes in front of Didymos. Also, the secondary occultation, where Didymos goes in front of Dimorphos, and also the primary eclipse, where the shadow of Dimorphos goes in front of Didymos. So during each of these mutual events, you can observe a dip in light in the light curves, and using this dip, we're able to find the time period of each of these separate mutual events. So light curves can also reveal the rotation period of an asteroid. So normally asteroids are mostly not spherical in shape, and this is because they're small enough that their gravitational pull is not strong enough to make them a sphere, which means that while the asteroid is spinning, we're able to see at some points more of the asteroid, some points less of the asteroid, as you can see in this animation. And from our point of view on Earth, we can observe how much reflected light we're seeing from the asteroid. And over time, we're able to get a curve, which will give us the rotation period of the asteroid. In this case, Didymos had a rotational period of 2.26 hours before the impact. So to get the light curves of Didymos, I followed a 7-step procedure. So I've already talked about these in detail at my previous presentation at RASC, but I'll go over them quickly. So first was finding telescopes located all around the world that could image Didymos. I had to create observation plans, while keeping in mind that I needed to observe Didymos with signal-to-noise ratio of above 100, so that meant I had to take the magnitude of Didymos into account and change my exposure time accordingly. The next step was pre-processing the FITS files. So this was to extract essential information from the FITS files so I can use it in the future analysis that I'll be doing. Third was plate solving the image. So this is matching the objects in my image to the objects in the sky gotten from catalogs such as Gaia. And after that, I had to select an aperture radius for both Didymos and the comparison stars. So I have to be careful while doing this, because if I selected too small an aperture radius, not all the pixels of the target object would be visible. But if I selected too big an aperture, I would include lots of noise in my observations too. So I had to find the kind of balance in between the two. The next step was finding comparison stars. So why are these useful? This is because stars have a known brightness that does not change over time, so it stays constant. So if there's any problems in the scene conditions, like if the weather is bad, I'll be able to know that from looking at the magnitude of the comparison stars. So these kind of act like the baseline for my observations. But finding comparison stars is hard because not all of them are suitable. Like some of them might be too small, some of them might have huge varying brightnesses over time. So it's really finding those 5-6 comparison stars in my image that will work out perfectly. The next step was actually generating the light curves of Didymos. One observation is not enough to get an accurate rotational period of the Didymos. So I've taken many observations and I've combined them together. But one thing I've taken into account while I was combining my observations was that I'd apply offsets to account for the change in the phase angle and the apparent magnitude of the Didymos. So how did the magnitude of the Didymos change before and after the impact? So here I have plotted a graph of, in blue, you can see here the magnitude of the Didymos as it would be without the impact. So this is computed by the NASA Horizons database. And in orange here is the magnitude with the impact, which I've computed myself from my observations. So pre-impact, you can see that my observations are very similar to observations from the NASA Horizon database. But as you can see, right after the impact, there's a change in about 1 magnitude. So the magnitude decreased by 1, meaning that the asteroid became significantly brighter right after the impact. And up to 2 weeks later, it still goes above the expected brightness before going back to similar brightnesses as predicted. So the curve that I just showed correlates with light curves from other sources, such as the Atlas Photometric server and a virtual telescope. And both during the impact, you could see a sharp increase in the brightness before going back a couple of weeks later to its original brightness before. So before the impact, combining all my observations, I was able to get a rotational period of around 2.259 hours. And this is very close to the expected 2.26-hour rotation period of the Didymos. And I was getting an amplitude of around 0.1. Amplitude is the total change in magnitude, so like the highest and lowest value, which was also correlating with the expected values. I repeated the same process post-impact, and I found out that the rotational period did not change at all. So stay 2.2599. And these are observations that I collected myself from 30th September to 26th October. So pre-impact, I was able to capture a mutual event. So as you can see in the above plot, there's one in the blue color, which is going slightly below the others. So this was the mutual event of, which was possible eclipsing. So post-impact, I wanted to try and measure the same things. So while I haven't been able to measure a definite eclipsing, I'm still analyzing some of my observations, like from the AAVSO telescope. And I think there might be a mutual event inside this, but I haven't finished analyzing it, so it's still to see. So what can the light curve rotational period give about the asteroid composition? So most minor planets have a rotational period above 2.2 hours, which means it does less than 11 rotations per day. But most of them actually exceed this limit by a lot, by going 4 to 10 hours a day. So why is this so? So lots of asteroids, especially the smaller ones, tend to be more like rubble piles with lots of with lots of loose rocks around, which means that they're held together by mutual gravitation. Which means that if they were to spin faster than what they're going right now, and if their rotation period were to decrease, then lots of pieces of these asteroids would be flung around. Which is why if an asteroid is to have a rotational period of below 2.2 hours, so it's spinning faster, then the asteroid has to be strand bound, otherwise it would fly apart. I'm going to give a quick example here. So let's say there's these grapes here. So as you can see, if I rotate it slowly, none of the grapes are falling. But if I start to rotate it faster, some of the grapes would fall apart, like it has just done. So the rotational period of Didymos is 2.26 hours, which is very close to the 2.2-hour limit. So this means that the asteroid spins quite fast compared to other asteroids. I'm going to give a comparison of two other asteroids, Ryugu and Bennu. So Ryugu has, it's about the same size as Didymos with a 900-meter diameter, yet it spins every 8 hours, meaning the rotational period is 8 hours, and it only does about 3 rotations per day. And Bennu, which has a much smaller diameter, also has a lower rotational period of about 4 hours, meaning that Didymos definitely falls on the higher speed category of asteroids. So while imaging Didymos after the impact, while stacking the images, I was able to see the tail of the asteroid, and I thought it would be fun to do some calculations. So I was measuring the length of the tail across time. So just measuring the length was using simple math calculations. So using the pixel scale, I was able to find the length of the tail in arc seconds. And then knowing how far the Didymos was to the Earth, I was able to find around a length tail of around 167,000 kilometers. Actually, I think I made a mistake here. It should be 16,000. I think I added an extra digit. But these are my observations of Didymos' sail after the impact. So you can see starting here at 27 September, when the ejecta hasn't had enough time to spread around yet, the tail is quite low. But at 30th September and 1st October, you can see that the tail length is increasing dramatically to go over 20,000 kilometers. But after that, it seems to be decreasing on 11th October, just to go back up again on 30th October. So I was quite curious about these changes because it seemed to be going up once, going down, and going back up again. So I was looking at information from the Hubble Space Telescope, which was also observing the tail of Didymos, the Didymos system. And it seems like it confirmed that the ejected material was expanding, creating the tail, and then faded in the brightness. But it also said that Didymos developed a second tail of ejecta between the 2nd and 8th October, as you can see in this GIF below. And they said that similar behavior is also seen in other comets and active asteroids. So a change in the Dimorphos orbital period. They expected a 73-second decrease in the orbital period, but it was fast 25 times to go to 32 minutes. So why the sudden increase based on the predicted to the actual? So using some of my own conclusions and from what I've seen, first I can see that Dimorphos is more of a rubble type asteroid, which means it's possible that when DART impacted it, it led to lots of debris escaping, as we have seen from the tail. But that means, like, for example, if you take a balloon and let out lots of the air, the balloon goes forward, which means that similar effects might have been seen on Dimorphos, meaning it would increase the speed even more. Also, since lots of the ejecta has escaped, it means the mass of the asteroid would be lower, meaning that the asteroid would be able to go faster, leading to a bigger change in the orbital period of Dimorphos. But in the future, changes in the heliocenter orbit will, from the Hera mission or anything else, will provide additional answers to these questions. So while doing the photometry, I had many challenges, especially post-impact. Because post-impact, the Didymos was now in a crowded star field because it was approaching near the Milky Way, meaning that many stars were in a path of the asteroid, meaning that the light curves I was getting was less accurate than pre-impact. Also, the asteroid is now moving towards the northern hemisphere, and all my telescopes that I'm observing Didymos from are in the southern hemisphere, meaning that I won't be able to view them for 1 or 2 hours every night. But pre-impact, I was able to view them for up to 4 hours. So I was not able to get as many observations. But in the future, I'll be looking for telescopes in the northern hemisphere so that I can get longer observations of Didymos. But also one other thing to take into account is that Didymos is now becoming dimmer. So right now it just dimmed above 16 magnitude, meaning that it's much harder to get a signal to noise ratio of above 100, meaning that they increase the exposure time to 2 minutes or more. Another thing that I noticed is even climate change is changing my observations, because for 6 days in a row, from around October 17th to October 23rd, none of my observations came, and this is in somewhere like Siding Springs. So I was really surprised, and it means that observing conditions are playing a big role in this. Right now, there is no probe or anything observing Dimorphos or Didymos, which means that all our observations are coming from ground-based telescopes, at least till the Hera mission comes in 2026. But before that time, now ground-based telescopes are what's needed, especially for measuring the shift in the heliocenter orbit of the Didymos system. Actually, someone has already been able to measure this in Spain. On the 18th of October, they were able to notice the occultation of the Didymos asteroid. And there's also more observations of the asteroid because actually from the Gaia telescope, because Gaia it takes lots of observations of the sky, meaning that actually on 4th November, it'll be taking images of the sky where Didymos is actually currently. So if any of you are interested in viewing that, you can. One last thing I want to mention, I've been also doing some just quick calculations for fun about the Didymos system. So for example, in the last image that showed both Didymos and Dimorphos, I was able to calculate the distance between the two. So I calculated 1,920 meters as the distance. The actual was 1,200. Also looking at the last complete image of Dimorphos on its own, I was able to calculate a diameter of 237 meters using just calculations based on the distance to the object, and the actual was 170 meters. And also looking at the images right before collision, I was interested in seeing how big the rubble was. It actually came up to 10 meters, which is quite big. So while all my calculations might have been overestimated, it was still fun to do these. If you're interested, I'll also be giving a presentation about my post-impact observations on the 25th of September at an iTelescope webinar. As before, I've submitted all of my observations I've collected on the AlphaDef website so that other people can see and use my observations. I would like to thank people who have helped me in this project. For example, Christina Thomas from the DART group, who has talked to me and given me lots of suggestions on my project. And also many other people like Daniel Parrott, who has helped me throughout and given me observations, especially pre-impact, that I've used. Thank you. If you have any questions, I'd be happy to answer them.
Arushi, that's an impressive undertaking and fabulous results. Well done. I sure hope you have time to do your homework because you're being distracted by all this fun stuff. Let's go to Emma. Do we have any questions for Arushi?
Yes, we got a couple of questions. The first question comes in from Blake Nancaro. He wants to know, are you using the BGO, the Burke-Gaffney Observatory in Halifax?
Right now, I'm currently not using that telescope. I've used it in the past for imaging Apophis, I think. But for now, Didymos, I have not. Previously, because it was not rising, Didymos was not rising in that area. But now that it's rising in the northern hemisphere, I definitely consider using the BGO telescope.
Cool. Thank you. This next question comes in from John's Garage. What is the composition of the asteroid?
That's a great question. So the composition of Dimorphos is not yet known, but more observations will definitely lead to a more accurate composition of this asteroid.
Great. Very cool. Thank you so much. That's all the questions we've gotten tonight.
Great.
Thank you, Emma. And thanks again, Arushi.